Well, I'd like to welcome you all to What Physicists Do today. Our speaker is Dr. Amy Furniss, who's from CSU East Bay, by way of Stanford. And before that, she was at UC Santa Cruz for her graduate degree, and she was a CSU alum, went to Humboldt State as an undergraduate. Her work is in this field of high-energy astrophysics, particle astrophysics. We see this throughout the series that one end of particle physics connects to another end of astronomy and these intersections. And sometimes the intersections are us, as we saw in the video presentation earlier in the semester, looking at LHC and looking at processes that happen at very high energies like the Big Bang, or that we get to some of these high energy processes in astrophysical phenomenon, which Dr. Furniss will talk about today. She had a wonderful story as we were chatting, as she was looking at the calendar of what physicists do and saying, I remember this, if I may say this story, I remember this being a high school student and seeing the list of talks that was happening at Sonoma State in What Physicists Do. And this was when you said at Eureka, so that was pretty far afield. And you knew you were going to be a physicist when you were talking to your father about driving you down here. And I'd like to think that Dr. Furniss's talk here today will stand as a way to bring more people into this field in the same way. And certainly we're all excited to hear her talk about a project called Veritas that I'm particularly interested in, and as I know, she's been in talks with our very own Dr. Kaminsky about these matters and the high energy gamma ray end of the universe. So this is an exciting talk today. Let's give a warm welcome to Dr. Amy Furniss.
Thank you for the introduction. Hi, everybody. So, as mentioned, I'm Dr. Amy Furniss, and so as a high school student, I really did try to convince my father, oh, it's just a 4-hour drive and just 1 hour long lecture on physics, and he's thinking, aren't you supposed to try to convince me that you want to go to some party in San Francisco? And I'm like, no, I want to go to a physics lecture. We never actually made it to a physics lecture, but I do remember those flyers in my physics class at Eureka High School. So they're part of the reason why I decided to study physics, but when I started studying physics, I realized that physics itself was not enough. I needed to expand my horizons. You know, physics, that's easy. Let's add astronomy to that. And so I became an astroparticle physicist. As an astroparticle physicist, I use astronomy and physics together, and this is not your standard telescope. So it is not an optical telescope in the traditional sense. It actually is a particle detector. It's the same thing that flies in space, a particle detector in Fermi, but this one is on the ground. And there's a couple challenges that come along with that I'd like to share with you. I've been with this experiment for quite some time now. As an undergraduate, I went to Purdue University at a research education for undergraduates, and I got to build this telescope, which was our first telescope. And it was kind of fun, except that it was in Arizona in the summertime, and you're putting mirrors on a telescope. So, you know, there was a lot of health concerns going on there, 107 degrees and shining light in your face. And since then, as a graduate student, I did some additional work. When I started as a graduate student, all 4 telescopes were operating, but we had to move one of them, which I'll refer to. We moved this one. It used to actually live behind that building. And then we've upgraded the cameras, which are actually these boxes right here are the cameras of the telescope. So I'll talk about each one of those things in detail. Just to give you an idea, this is a building. These are cars. So these are very, very large telescopes. And their mirrors are tessellated. They do not have to be smooth mirrors because they're not optical telescopes, and they don't operate in the same way that those standard optical telescopes do. So I'm going to break the talk up into 3 parts, and hopefully I don't have to speed through this last part. If we do run out of time, I'll just touch briefly on this last part, which is a nice extension of what I'm doing. But I want to talk about, well, what does it mean to be very high energy? Is it high energy? Is it just gamma rays, or are they a special kind of gamma ray? And then how you actually study the very high energy sky using Veritas. So after I talk about that, which is kind of a significant portion of this talk, Then I'll touch on what I study with this instrument particularly. This is an astrophysical object. They're blazars. You may know something about them if you've actually worked with Lynn and Fermi. And so we'll talk about what blazars are, why they're interesting in perspective of very high energy gamma rays, and how they actually work, at least what we think of how they work, although we're not sure yet, and there's still additional studies that need to be made. So they're interesting astrophysical objects to study on their own, but they're also a gateway to be able to study some larger fundamental questions of the universe. And so you can extend these studies to cosmological questions. So you get to understand what these blazars are, as well as when you understand what they are, you actually have access to a lot of other science. And feel free to interrupt me at any time throughout the talk as I am going through these concepts. They seem fundamental and boring to me, but it's because I stare at this stuff all day, every day, and it's going to be new to you, so please raise your hand and say, wait a minute, you're spouting jargon, please explain more. All right, so this is a Veritas telescope. This is telescope 1, and it's at its very beginning of its life. It doesn't even have all of its mirrors here. And Veritas stands for Very Energetic Radiation Imaging Telescope Array System. So instead of trying to say that 5 times fast, we just call it Veritas, which stands for truth in Latin, but I don't think it's related to why we called it that. We just had these letters that we needed to work with to make a name. Veritas is located in Arizona. This picture comes up a little better on my screen than you can see it, but if you climb up a mountainside right outside of base camp, you're looking at the Fred Lawrence Whipple Observatory, and Mexico is right over here. Tucson is about 80 miles this direction to the north, and you can see those 4 telescopes that are quite large, the building, the administration building right here in the center, and these telescopes are sensitive to photons that have energy of 100 GeV to 30 TeV. I'll tell you again what that means. This is just what particle physicists and astrophysicists at the high energy spectrum like to refer to as the energy range that we're studying. And the instrument is capable of 15 to 20% energy resolution. Okay, so what does that mean? It means that if we detect a photon and we say that it has this blank energy, we're not that sure plus or minus 20%. So as you get to higher energy, that means that you have a higher uncertainty in how much energy that photon had. So it's kind of looking at the universe and not being able to say exactly what that photon was, but we have pretty good energy resolution. We don't have as good angular resolution by any means by optical telescopes, but in terms of smaller instruments that fly in space like Fermi, our resolution in space is really quite good. And this instrument has gone through a very interesting lifetime. It's started operation in 2007, full operation with all 4 telescopes. And since then, we have moved the telescope. So this is a telescope. It was located over here. And located over there, it wasn't as sensitive as it could possibly be, the array, so we moved it over here, and that was a huge endeavor. We did that in 2011, and we have since then also upgraded those cameras to higher efficiency cameras that I'll talk about. So let's go back to this number right here, 100 GeV to 30 TeV. This is not joules, the standard measure of energy that you're used to in your SI units, but it is a measure of energy, and it's the measure of energy of the photons that this detector is capable of or is sensitive to. So this is 1 eV. If you take 1 electron and you accelerate it across 1 volt, you will get something that has a certain amount of energy of 1 eV. If you look, we've got energy of a visible light photon is just about 1 eV. So those are the photons that are hitting your eyes now. Those are the photons that optical telescopes pick up. Now let's multiply that by 1 billion. What do you get? Oh, you get a gamma ray that has an energy of about 1 GeV. That's a light bulb, which is 1 eV. Multiply that by a billion. There's a lot more energy in each single one of these photons that we're actually detecting. So let's talk about just this first part. What does it mean to be very energetic radiation? Well, we have an electromagnetic spectrum. This electromagnetic spectrum is far greater than what we can see with a visible eye. It's just because the sun emits light at a certain energy, we have visible that we're sensitive to, and visible is coming through our atmosphere, and it has a wavelength. It's a little wave packet. It has a wavelength that's about the size of little protozoans. And it corresponds in the universe, if you see these types of photons, you can think physical processes that are happening around 10,000 Kelvin, which that's pretty high. This is plus or minus. We have blue photons, we have red photons. They're all different energies of photons, but this visible light, it represents a very small sliver of what we're actually able to detect now that we have additional science. We also have, or additional instruments. We also have radio, much lower on the energy, so as you go from the left to the right, you're increasing in energy. We have radio waves, the same kind of stuff that your car picks up if you have a very old car, your AM and FM, and you can move up to infrared, visible, and then going up higher than our eyes are sensitive, ultraviolet, X-rays, and gamma rays, and as you increase in energy, the wavelength gets smaller. The frequency gets higher, and that's so that you can always multiply those two things together and get the value of C, because photons travel at the speed of light. And you can also see what kind of physical processes or what kind of temperatures you're looking at when you're emitting photons in the radio through the gamma ray band. Gamma ray astronomy is a relatively new field. Optical astronomy has been around for a very long time because we've had our eyes, so we've been able to look up at the sky and say, there's a star, there's a star, there's a constellation. But we haven't been able to use our eyes to look up and be able to detect gamma rays or X-rays or radio waves, so we had to wait for the advent of technology to come up with a way to look at these things. And it wasn't just until 1989 that we were able to detect very high energy gamma rays. So what types of processes led to these kind of photons out in outer space, out in the universe, we weren't sure about. But there was theory that say, okay, well, if there's non-thermal processes, meaning very, very energetic processes, the acceleration of charged particles in intense gravity fields, strong magnetic fields, or relativistic particles, there's potential to actually emit photons with 1 GeV or higher of energy. So we started looking, and it actually took the first detection of a source took a lot of patience. It was one group down in Arizona at the Whipple Observatory. They worked for 20 years. No detections, no detections, no detections. They were very patient. I think there's a lesson somewhere in there. And eventually, they got a nice detection, and it opened up this field. And when I started in June of 2009, this was the entire gamma ray sky above 100 GeV. So this is above the prime energy level of the Fermi telescope, which is up in space. And you have some galaxies here, which are in red, and this actually represents the galactic plane. So the galactic center is right here, and the north pole of in galactic coordinates and the south pole of galactic coordinates, and this kind of wraps around, so this part of the map would attach to that part of the map if you were able to wrap it around the side of your head. So let's actually fast forward just 6 years. And this is now the field of gamma ray astrophysics. These points represent sources that have been detected by instruments such as Veritas, and each different color represents a different type of source, and we're trying to understand the astrophysics that's behind each one of these sources. So as I mentioned, this was the galactic plane. The galactic plane is relatively crowded, and you can guess these are galactic sources, meaning they're sources that are within our own galaxy. So coming from 2 neutron stars, or a neutron star and a white dwarf, so a binary system, some relatively extreme scenarios. Outside of the galactic plane, we're actually looking farther out beyond our own galaxy and looking at other galaxies that are emitting these very high energy gamma rays. So those are much farther away, and so they have to be a lot brighter. So you have to ask yourself, what kind of physical processes are leading to these extraordinarily high energy photons that are traveling so far to reach us, and there's enough of them that we can detect them with our piddly little detectors here on Earth. So just to give you kind of a rundown of what type of gamma ray sources we're looking at, and we're going to go all the way down from this left-hand corner up to the right-hand corner, from very close to us, so local within our own neighborhood, extending out to very far away to even other galaxies. And so you've got terrestrial gamma ray flares. These are kind of low energy, the sun, and we also have pulsars, so that's a neutron star that has a jet coming out of it and is spinning relatively fast. Gamma ray binaries, supernova remnants, so stars that die, they explode, and their shell, as they extend out, actually produces some gamma rays. Globular clusters, There's the Fermi bubble, so this is looking at our galaxy, the center of the galaxy, and you can actually see some gamma ray halo coming out that looks like it's a flaming candle on either side. Still don't quite understand what is leading to that. So this is all kind of within our own little galaxy, the Milky Way, and then we get farther out and you start looking, okay, well there's the Large Magellanic Cloud, there's blazars, there's gamma ray bursts, there's radio galaxies. So these are all different types of galaxies having all different types of processes that could lead to their gamma rays that we're looking at today. These are all astrophysical sources, so all of these gamma rays are traveling some distance to get to us. There's not very many sources of gamma rays here on Earth. We have lightning. Lightning produces gamma rays. There's these really unfortunate explosions. They also produce gamma rays. Nuclear radiation, and then there's interaction with a gamma ray with the atmosphere. You can produce these showers. So, well, let's talk about how we're actually detecting these. We detect them with an imaging telescope array system, and I showed this plot earlier, and I concentrated on this plot. Did anybody notice anything about this plot that might pause as to why we spent billions of dollars to put a gamma ray detector on the Earth? Let's look at the top. The atmosphere is opaque. So we have spent quite a bit of money to put a gamma ray detector on the ground below the atmosphere, and the atmosphere is blocking these gamma rays, luckily, from coming through the atmosphere. So, you know, astrophysicists, they're relatively intelligent, and they probably have a reason for this. So let's explore why we put the detector on the ground and one in space. We have one in space, and you have to mention it because it's the other portion of what gamma rays are. They're lower energy gamma rays than Veritas is sensitive to. You're probably all familiar with Fermi and its energy range. It's up in space, and so it doesn't have the problem that those gamma rays aren't making it through our atmosphere because it's above the atmosphere. So they're not blocked, but it's only a 1 square meter. It's an itty bitty baby telescope. Very expensive to send to space, but it's still a very small telescope. And it works as a particle detector as well. So an interaction with a gamma ray comes in, and that gamma ray breaks into an electron and a positron. You can track the electron and the positron, and you track it through what the tracker is. This is actually the telescope. It doesn't look like a standard reflecting telescope because it's a particle detector. And you can determine where on the sky that gamma ray came from and how much energy did it have. Well, we can't send Veritas into space. That would be exorbitantly expensive because of the relative size. So how are we detecting gamma rays on the ground if you have an atmosphere that is blocking them? Well, we don't actually detect gamma rays. Oops. We detect secondary showers from gamma rays. So what happens, the gamma rays don't just disappear when they interact with our atmosphere. Physics doesn't allow that. There is a conservation that has to occur. And when that gamma ray interacts with our atmosphere, it interacts with a nucleus in our atmosphere and breaks into an electron and a positron. That electron and that positron have so much energy because you have a gamma ray photon. That gamma ray photon has to break into an electron and a positron. And so if you have enough energy, not only do you have the rest mass of the electron and the positron, but they'll also have enough forward kinetic energy moving forward through the atmosphere greater than the speed of light. Who has a problem with that sentence? Willie, that's great. You're all very open to that. I had a very big problem when I was told as an undergrad, oh yeah, well we're just detecting these showers of particles moving greater than the speed of light. It's like, wait a minute. Wait, everything I've been taught. The rule is that you can't move faster than the speed of light in vacuum. At least so far as we know, that is the ultimate speed limit. But the speed of light slows down when you're in a medium. Our atmosphere represents a medium, and therefore these electrons and positrons they can't move above c, but they can move above how fast the speed of light moves through the atmosphere, which is c divided by the index of refraction of this medium right here. Of course, nature doesn't really like that, and it causes the same thing as happens when you move faster than the speed of sound in one of those really expensive airplanes. You produce a sonic boom. You're producing an analogy of a sonic boom here, but with light. So you produce gamma rays or photons from that shower, and those photons, it's kind of it's serendipitous that those photons happen to be blue, visible light that our eyes would be sensitive to. So then, okay, we have electrons and positrons that are moving through our atmosphere. They're going faster than the speed of light, and they're shedding energy in the form of blue light. We can get an optical detector to reflect that blue light, focus it onto a camera, just like optical astronomy. Once we have information about that blue light, we can actually study the photon that originated in that shower that we're talking about. So what you look at is this shower is very large. If you put a reflector, an optical reflector down here, you have a very high energy gamma ray about 20 kilometers above the sea level. It interacts, produces this cascade, and this cascade will then produce a blue light cone. And you have a light cone that comes down, and that blue light cone, this is referred to as Cherenkov radiation, and it occurs when you're moving through the medium faster than the speed of light through that medium. And it's kind of like a bow shock. It comes at a well-known angle and is very well described in terms of the particles that are coming out of that interaction with the primary gamma ray and the top of the atmosphere. The one problem, though, is you could say, okay, let's collect all of this light from this shower, and then we'll know all about this gamma ray, and we'll be able to trace this gamma ray back, and we'll be able to know everything about gamma ray astrophysics. How easy. Let's all do that and then go home. Well, it's never that easy. Of course, it's never that easy. There's a lot of background. Unfortunately, we have the same kind of interaction happens if an electron or a positron or a proton or a heavy nucleus, any charged particle that hits our atmosphere that has sufficient energy is going to cause a very similar air shower and blue light. So we could misinterpret and say, oh, we just saw a photon, a gamma ray photon, but it wasn't a gamma ray photon. It was what's called a cosmic ray. And these cosmic rays, which are charged particles from astrophysical sources, it's very difficult to do astronomy there because there's magnetic fields that bend those charged particles away from their original path. So you can't take a charged particle and say, oh, it came from that direction in the sky, because it only came from that direction in the sky because the magnetic field had bent it into our line of sight. So you can't say the source is in that direction of the sky. So these are troublemakers, and they're everywhere. They decrease as you go up in energy. So there's about 1 particle per square meter per second if you're down at the low energy end. But if you go up to the higher energy end, 1 particle per square kilometer per year. So you have this background that as you go higher in energy, it's going to be more troublesome, and we're operating around this kind of energy. So we have quite a few of them. We have more than this number, but less, luckily, than that number. So let's look at how we can tell whether it's a photon that hits our atmosphere or a charged particle that hits our atmosphere. Remember, the photon is what we're interested in. The charged particle is something that we want to throw in the trash. If you had special glasses on where you could actually look at these showers, this is a gamma ray photon. It interacts with the top of the atmosphere, and we're moving down through the atmosphere. Let's say this is sea level. These red lines represent electrons and positrons that are produced in this cascade air shower that actually occurs. Here you have a proton that hits the atmosphere, and that proton has more transverse momentum. Because it has more transverse momentum, your shower is not as well contained as in the vertical plane right here. Instead, it kind of spreads out more. So I like to say this is well contained, and this is a little more chaotic. Let's actually switch our focus, switch our perspective for just a moment, and let's imagine that we had special glasses on that allowed us to see electrons and positrons instead of just blue light. And not only could we see electrons and positrons, let's say we can see muons, and we can see protons, we can see pions. We're going to put these special glasses on, and we're going to come out, lay down, and look directly upward at these showers as they progress. We have a movie that I'm going to show, and I'm going to show you the difference between how one of these would look staring up from the ground, if you could see those particles, and how one of these would look staring up from the ground if you could see the particles from that shower. So this is a gamma ray initiated shower, and blue represents electrons and positrons. So there the shower has started. Hopefully you guys can see that. These are all electrons and positrons. It's growing. This is its elevation above sea level, so it's coming down closer to you. And you can see it grows, and then at some point it reaches a maximum and then kind of dies out a little bit. And this is the shower that you're looking at. Remember those electrons and those positrons that are moving through our atmosphere and releasing that blue light because they're moving too fast for nature to be comfortable with. Now, we're going to put glasses on. So that's electrons and positrons are blue. Now we're going to have yellow representing muons. You didn't see any muons here. We're going to have green is going to be pions and kaons. Purple is going to be protons. You didn't see any of those here. What was the only color that you really saw here? Which was electrons and positrons. So they're relatively clean showers. So this is going to be a shower that happens when a proton hits the top of the atmosphere. It's like a rainbow, confetti. You've got some protons or some muons here in this yellow, and all the blue. You have a few electrons, lots of muons. There's some green in there, that's pions. There's a few red in there, that's protons. And you can see it covers, it's not just concentrated right there in the center, it covers the whole screen. So these are much more spread out, and then you have a whole bunch of little cores of these electron-positron showers that are all over the place. And remember, this is what we don't want to pay attention to. We want to pay attention to the showers that are cleaner, that are gamma ray events. Kind of dies out in the end very similarly to the other one dying out as you move closer to you, as you're laying down looking directly upward at the sky. So how we actually detect these sort of things, you might imagine, well, why can't I go outside and why don't I see these kind of showers with my own eye? It's blue light. I can see blue light with my eye. Can we turn the light back on? Sorry. I can see blue light with my eye, so why can't I just go outside and look? That seems like it would be a lot cheaper than building some of these instruments that are capable of detecting the gamma rays. Well, the blue light is very dim, and there's a lot of background light. Even if you're in the mountains in the Sierras, there's a lot of background light from blue starlight and light within our atmosphere. And they're very, very, very fast developing showers. These showers develop from the top of the atmosphere to the bottom of the atmosphere in about 15 to 20 nanoseconds. So if you have that type of resolution with your eyes, then you should contact the government. They probably want to know about you. So how do you detect these showers of blue light? Well, you need the mirrors, and the mirrors can actually reflect the blue light. So we have this mirror right here. It's reflecting the blue light, and it's reflecting that blue light into this camera. This is the first gamma ray. This isn't a Veritas telescope. This is the first gamma ray telescope of its kind. It's referred to as Whipple, and it was in the same location in Arizona. If you could take a little mount up here and stand right here and look into the face of the camera, this is what the camera looks like. So you have your camera box. It has to remain very dark. We open the shutter, and you see pixels. These pixels are each one of those circles, if you can make out the circles, each one of those circles is about 1 inch in diameter, and they are actually photomultiplier tubes. They are not standard CCD that you use in optical astronomy. They're photomultiplier tubes, so they're very sensitive to dim light. And they're very, very fast. So they have the ability to resolve events, these photon events, that are of 15 to 20 nanoseconds long. Very fast events. How they actually work is if you have a blue photon, which is resulting from Trankov light, it comes and it hits what the photocathode here, and it pops off an electron. So then you have an electron, and there's a voltage that's dropped from here to here. And that electron really wants to get over here. So this is positive charge, or positive looking, negative looking. That electron doesn't want to be over here. It wants to make it down here. But we put dinodes in its way, and dinodes work to produce an electron avalanche. So even though you have one photon that hits here, that one photon will produce one electron. That electron will hit a dynode and release multiple electrons. Now, instead of just one electron, very hard to measure, you have multiple electrons. Those multiple electrons, again, they really want to make it over here. They hit another dynode. There's multiple electrons for every single one of those electrons. And you can end up, for one photon hitting here, you can end up with about 1 million electrons. 1 million electrons at the end, you can read that as current with electronics. So that's what we actually read. We read the current. And you can, just to show you how fast one of these events actually is, this axis is in nanoseconds, and it's running from 0 to 40, and this is the time that the photons are actually hitting the camera. So just between 5 nanoseconds and 15 nanoseconds, we see current. And it's normalized to an amplitude of 1 just to keep things reasonable. But we see kind of a relatively high current in that period of time.
On that lower right quadrant, there's a glitch in the shoulder. Is that an artifact in the instrument?
Here?
Or is that actually happening?
That's very good eye. So this is one way that we can actually determine whether or not it's an event that we're interested in. So the showers will develop in a way where you have a slight shelf here that you won't see with a cosmic ray shower. There's much more of a drop, and then there's more events here. So yeah, that's real, and we do pay attention to that with our analysis. Okay, so again, looking up at those showers and integrating all of that shower, all of those photons that we would have seen that were resulting from the electron and the positron interacting. We look at a photon, and it's nice, spherical looking pancake, and on the camera, this is what it looks like on a little ellipse. Self-contained, not very many PMTs. These dots represent the amount of current that photomultiplier tube is actually picking up, so the number of photons that have hit that. And you can fit an ellipse to this event, and then we'll draw a line that goes along that semi-major axis of that ellipse. I'll show you why in a moment. Here you have your proton. It's all over the place. Got much dirtier picture here. It's not a nice ellipse. It kind of looks like it has a ring behavior. That ring behavior right here is actually because it's a muon. And that's particle physics for you, is that we can recognize that this is not a gamma ray event, that it's actually caused by a charged particle because it has a certain shape. So we look at this event, and we have algorithms that look at this event, and we say, that's garbage, that's good. Throw that out and keep that. So this ellipse doesn't have a very nice fit to the image in the camera. And we use that fit in order to determine whether or not we want to keep it. So as I mentioned, we fit an ellipse, and then we draw this nice line along the semi-major axis of that, and we have 4 telescopes, not just 1 telescope. So if you take the optics into account and the geometrical effects of having a reflector, you have 4 events. Now we have all 4 telescopes. This is T1, T2, 3, and 4. And because of where they're located, if the shower hits in the middle, they'll see these showers from different perspectives. It's always nice to get additional perspective. And you can trace those lines of semi-major axis, and they'll actually trace back on the ground frame back to where that gamma ray would have, if it hadn't interacted with the atmosphere, and if it had gone straight through the Earth, where it would have hit the Earth. So then we can use information about how this ellipse looks, where it hit on the Earth, to be able to trace it back and say it came from exactly right there in the sky. Oh, there happens to be a galaxy right there in the sky. Maybe they're coincident, or maybe it was a background photon. Yeah.
Is it as simple as there's this distribution, you're showing us cuts, but if it's coming at an angle like this, it's extended that way, and so so you see that, and you get one of those from each of the 4 telescopes.
Yep.
To draw this.
Yep. Okay. So how do we actually? So we can tell, taking these 4 perspectives, where it hit on the ground and the shape of the ellipse in the camera. For all 4 of them, we can figure out where it's coming from in the sky. That's a very important piece of information. Not only do we want to know where it's coming from in the sky, we want to know how energetic that photon is. Was it 100 GeV? Was it 100,000 GeV? We need to know whether it's a baby gamma ray or a daddy gamma ray, I guess. A big energy gamma ray or not a high energy gamma ray. And we do that just by measuring the amount of light that we're collecting. So if you have a very, very energetic gamma ray hit the atmosphere, that energetic gamma ray is going to produce more electrons and positrons, and therefore more blue light, and we will collect more blue light. So that's here, higher current, higher amount of light, there's more shower particles, the primary gamma ray had more energy. If it's relatively dim, it will have low current, that's low light, there's not very many particles in the shower, and therefore it was a low energy primary. And we have this down to a science, joke intended, in that we can do it to within 20%. We know how energetic these these photons were when they interacted with our atmosphere. So now we have information about where on the sky the photon came from and how much energy it had. So these are our main science products. This is obviously an artistic color scheme. You can't see color with gamma rays, and so we have to provide some amount of color to the intensity map. This is if you were to look on the sky with glasses that allowed you to see gamma rays, you would see a lot of point sources. This is what we call as a sky map. There is some low number of counts that are coming from around here. Those low number of counts are just background gamma rays that we're reconstructing to be coming from different parts of the sky, but there's way more gamma rays right here. And that's significantly more gamma rays so that we know that that is a source. We're also collecting information about how many photons the source is putting off in energy. So if we start at 100 GeV and go up to 10 TeV, you can get the number of photons in that energy bin. So this source represents something that puts off far more. This is a log scale, so 10 times, 20 times, 100 times more photons here in the low energy bins than in the high energy bins. So it's kind of running out of power as the physical process extends to higher energies. This amount of information is sufficient for us to be able to guess and produce some studies into what is causing these photons to begin with. Okay, does anybody have any questions on the technique before I touch on what I study with this instrument?
Can you go back to the previous slide? So you show the decay here, and I wonder at what point the curve essentially will have to stop and become lower and lower, or does it just keep going?
I'll show you that. Very good question. Thank you for the lead-in. I'll touch on that. So physical processes, you can't just have this run away forever and ever and ever. That would be interesting, but there is a turnover point here where the source has to turn on in gamma rays. And at some point, once you get enough high energy, what we're finding is that they decay. They don't follow this nice straight line. It looks like they just fall off completely, and the progenitor of these gamma rays has just completely run out. So there is an energy limit that we're finding.
Yeah, and one more thing. When you say low current versus high current, can you give us some idea how much current we're really talking about, in terms of low or high?
Each PMT, the photomultiplier tube, would have somewhere between 2 and 10 microamps. So, and then you integrate up those microamps in each photomultiplier tube to get a relative charge out. And that relative charge is proportional to how much energy the original gamma ray had.
That's a pretty high current.
It is a pretty high current, yeah. But that's due to the voltage, where we really turn up the voltage and have that avalanche of electrons optimized to give us as many electrons, because it allows us more sensitivity. Okay, so I use this instrument not only as studying the instrument itself, a task, but I use the instrument in order to study blazars, which are a special type of galaxy. And in the very high energy band, they're not that special. In fact, they have been called by one of my colleagues the scourge of the sky, which is a little insulting. But they're relatively commonplace in a field which only has about 150 sources. About 100 of those sources are blazars. And so not only will I tell you what blazars are, we'll touch on how blazars are thought to emit these high energy photons. So blazars are a type of galaxy. They're a special type of galaxy for multiple reasons. Number one, they're active. They have supermassive black hole at the center, and they have jets emerging relatively perpendicularly to the plane of the galaxy. So this is a quasar, you can see, which is an active galaxy. You have a supermassive black hole at the center, and there's jets emerging from there. These are not just, I don't just study quasars with Veritas, I study blazars, and blazars are a geometrically selected subset of these where you're looking down the barrel of the gun, so directly along that jet. And so it's very similar to if somebody's shining a flashlight into your face, it looks bright. So you can't really study a lot about the host galaxy, so all of this stuff around it, you really just have to get the amount of light from that center you're looking and mostly studying the jet and the emission arising from that jet. So they're powered by supermassive black holes, and the energy is high enough that it doesn't correspond to a temperature of a process in astrophysics. It's beyond that, and it has to be relativistic particle population. They all produce this relatively interesting, what we call a spectral energy distribution. That's jargon, so let's ignore that for a minute. What a spectral energy distribution is if you study in frequency, so as energy increases to the right of photons released from these objects, down here you're looking at radio, all the way up here you're looking at gamma ray, and it's a measure of how much power in each band these sources are putting off. So you can see that in radio, they have a relatively low amount, they're releasing a relatively low amount of power, in optical more, and then they fall off in X-ray. And this is your turnover that you were referring to previously. They don't just keep going up and up and up forever and ever. There is a turnover, and this right here is where Fermi is sensitive, and this is where Veritas is sensitive. So we always get the falling edge of this, what I'll refer to as SED. There's a challenge, additionally, yay, more challenges, to studying these sources because you can't just look at them once with radio and then 5 years later look at it with an optical telescope and then 6 years later look at it with a gamma ray telescope, because every single one of these bands is variable, which means you look at it and it will be brighter or dimmer than it was the previous time you looked at it. So this is just displayed here. We're showing a light curve of snapshots of how bright something is. This is in X-rays. You can see that it's dim here. A couple days later, it's very bright. A couple days later, it's very dim. A year later, it's very bright. This is the Fermi lat. Very nice coverage because they see the whole sky every couple times, or a couple times a day. And the Fermi lat also shows this variability. And then whenever we take a picture of how bright it is with Veritas, you can see it was very bright, then it's dim, then it's bright, then it's dim. So you have to look with all of these instruments, a radio instrument, an optical instrument, an X-ray instrument, and a gamma ray instrument simultaneously. So not only is it a challenge technologically to get all of these instruments working, it's a challenge like herding cats, getting astronomers to work together and get all of their telescopes pointed to the exact same part of the sky for the same period of time and taking the pictures of the exact same source. And then, on top of that, once they have the data, trying to get them to communicate and extract science from those. So, lessons, dealing with people, yeah. All right, so this is a spectral energy distribution. I was showing a cartoon representation. This is standard for all blazars of what they look like. There's a little bit of differences. These peaks can shift to lower or higher energy, but these double peaks are very common. This is actual data, so you can see clearly there's two peaks. Radio data is right here. You have optical data right here. X-ray data is right here. This is Fermi data, and this is Veritas data. And these lines represent a model as to what we think is producing the emission that we are observing. We have a theory that this peak, right, all the emission that is coming in this energy range, so from radio up to X-ray, the photons that are being emitted there are coming from a strong magnetic field and then charged particles within that strong magnetic field. If you have a charged particle in a magnetic field, that charged particle is going to change its path, the direction of its path, not necessarily its velocity, but changing the direction of its path is acceleration. Acceleration means emission of energy, a photon. Then here we have inverse Compton emission, where you're used to Compton emission, maybe if you've taken a modern physics class, where you can have a low energy photon coming in or a high energy photon that gives all of its energy to an electron. That electron has more energy. In inverse Compton, we have a low energy photon, say an optical photon comes, there's relativistic electrons hanging around, for what reason we still don't know, and that low energy blue photon hits an electron and then comes out as a gamma ray because it steals all that energy away from the electron. So energy conservation says this interaction, the energy has to be conserved, and so the energy is being given from that electron to the photon, and you get gamma rays. Well, what kind of physical scenario will have a high magnetic field and relativistic electrons? What we think is happening, I've made a really nice artistic rendition here, is this is your black hole, and this is an accretion disk, so very close near that black hole. All of this stuff is swirling around, eventually going to fall into that black hole. This is your jet that you're looking at, and this is us on Earth looking down the jet of these galaxies that are very far away. We know that there seems to be jet, and within those jets there's these blobs. And we're relatively sure because we can look at these objects that are not aligned directly toward us, but are instead aligned to the side just a little bit. This gives you, one of those is M87, it's very famous, and it's radio observations. You see, look, there does seem to be blobs of higher energy emission. And those blobs do seem to correlate. This is X-rays, optical light, this is the Hubble image, and this is radio observations. So we have observational evidence that these blobs really are there. Now what are these blobs that are moving down the jet? These blobs, if they were blobs of relativistic electrons, they could lead to this type of emission. So these relativistic blobs, not only are they filled with electrons and positrons that are moving close to the speed of light, how they got to that speed, don't ask me, I don't know yet. But they are also moving with bulk motion. The whole blob is moving down the jet at close to the speed of light. So you have a lot of energy in this particle population here. We also have some outer material here, and that outer material is just stuff that has not yet swirled into the black hole. It's referred to as the broadline region. So one of the main open questions is, yeah, we can explain what we're seeing in the gamma ray band and the radio and the optical with this model. But one of the open questions is, where do these come from? Why do we have a black hole and a jet emerging from that black hole? It seems a little counterintuitive if you have a black hole and then you have energy that's coming out, not out of the black hole, but out of the vicinity where that black hole is. All right. There's one additional piece of theory that people keep picking up and then dropping and saying it doesn't work and then picking up and dropping it. And this is where astroparticle physics really does come together. You have to be a particle physicist and an astrophysicist to understand this. But you could, instead of having just electrons and positrons, you could have some very high energy particle interactions going on. So protons interacting with gamma rays to produce electrons and positrons, or producing a couple interactions that result in pions, and pions decay into gamma rays. The details here are not important, except the fact that you can produce the exact same type of emission with protons. So we have two very different theories that are going on. All right, so I'm almost going to finish up here. We have very high energy blazars, so let's assume that we understand everything about very high energy blazars. Don't worry, you're not out of a job yet. There's a lot to learn. You get to study fundamental laws like particle processes at high energies. Nowhere else in the universe do you get particles that are at this energy. You cannot produce them here on Earth. You do not want to produce them here on Earth. You want to keep that laboratory as far away from your little safe Earth as possible. So it's a good thing that they're in galaxies very far away. You can study questions, open questions like Lorentz invariance. There's a theory that once you get to high enough energy, the speed of light is not constant. And we can't prove that here on Earth. We have to have laboratories where there's cosmological, very large distances between the photon producer and the observer. You can study where these charged particles that I was talking about as our background are coming from. And you can even look for exotic physics, which everybody loves to concentrate on these. These might give us evidence or might give us proof against the existence of axions, which have been proposed as dark matter candidates. You can study cosmology, which I'm not going to have time to get to, but you can study this, use these sources in order to understand how the universe has developed from the Big Bang to us today, and how fast things clump in the universe, meaning how much dark matter there is. You can study the intergalactic magnetic field, so that's not the magnetic field here within our solar system. It's not the magnetic field of our own galaxy. It's the magnetic field that extends between galaxies. So this magnetic field is, first off, going very, very, very far distances, but it's also a question of why do we have a magnetic field between galaxies? how did this intergalactic magnetic field start, and how is it changing over time, and what is its role in the evolution of the universe? And then, of course, there's these very standard in terms of astroparticle physics, lessons that we can learn about black holes, which are curious objects in their own. You can learn about what produces a supermassive black hole, and the jet physics, why that jet emerges from the vicinity of the black hole, and how the black holes evolve and change the galaxies of which they're in. So I was going to touch on using the blazars in order to study the extragalactic background light and then constrain the cosmological evolution, but I don't think that I have time for that. I'm not sure.
We go to the hour.
You do go to the hour.
Yeah.
Okay. Then before I move on, is there any quick questions about what blazars are? I'll try to make this quick without making it completely vague.
Can you talk a little bit about that beaming angle that at some level you might be finding what that beaming angle is, but is there do you see that correlated with the energy of the showers? Is this something that you're looking at, and can you talk about that observationally?
Observationally, that's an excellent question. It is a huge challenge because these sources, in order to get that relativistic beaming effect and make these sources very, very bright in gamma rays, appear very bright in gamma rays, these sources are so beamed and so far away, they just look like point sources. So we can't tell if the jet is directly aligned with our line of sight or 5 degrees off our line of sight, or if the opening angle is even 1 degree, 2 degrees, 10 degrees. So that's one thing that we want to study, but without having an instrument that has better angular resolution, it's just out of our reach right now. But it would be a very important piece of information to throw into the questions.
The first part of your talk, you talked about when you move one of the 4 telescopes a couple hundred meters, the sensitivity went way up. Why would it?
That's an excellent question. So you have these pools of light that are coming down from these showers. And you want to look at these showers from 4 different perspectives. So we had 2 of the 4 telescopes that were sitting close enough that they saw the same perspective of that shower. So we couldn't, when you drew the lines through that ellipse in order to determine where would that cascade have actually hit on the ground, you effectively only had 3 telescopes. So even though you were collecting the light with 4 telescopes, you didn't have the ability to determine exactly where that photon was in the sky as well. So we moved it far away. So they're all about 100 meters. The baseline is about 100 meters. So now we have, for a majority of the events that we see, very nice perspective that's equally distant for each of the telescopes.
You're going to build one.
You're going to build one of these? I'll use it. You build it, and I'll use it. We'll Nobel Prize in our future. All right, so let's talk about using these very high-energy blazars to constrain the cosmological history of the universe. It's always fun to say at a bar. People are like, oh, what do you do? And I'm like, oh, I study very high-energy astroparticle physics to constrain the cosmological evolution of the universe. And then they turn around really fast and run. No. So it's very much of something to say, but what it means is we had the Big Bang, and now we have the universe today. How did it get from the Big Bang to where we are today? And how does dark matter have anything to do with that? So it would be really nice if all of the photons that our galaxy, our blazar, produced, and in the very high energy band, it would be very nice if all those photons traveled very nicely directly along and got to Earth. But that's not very good job security. Physics is always more complicated than you want it to be. So the bottom line is that no, not all these photons get from the source to us. Let's explain why. This is, again, particle physics. So we have the universe has been produced from a Big Bang, at least we theorize. There was a Big Bang, and then the universe has since inflated. We've had some structure formation, galaxies and stars. And so once you have matter that clumps up enough to produce stars, those stars start burning and producing their own light. And that light is usually in the infrared or the optical or the UV, depending on whether it's been emitted primarily in the blue light or if it's been absorbed by dust and then re-emitted in the IR, so the red zone. So these photons, when they're produced by stars, since the beginning of the universe all the way until where we are now, these photons, what happens to them? they float off into space, and then they're just there. So we have this box of a universe that continues to fill with photons from the photons produced from stars. So if stars were to form very early on in the universe, you would have more time to produce this fog of photons. If you had stars forming very late in the universe, you wouldn't have a very dense fog of photons because there wouldn't be as much time for these stars to produce these photons. So if you could measure the density of this photon fog from stars, you could figure out when stars started forming. And stars will start forming and matter starts clumping based on dark matter and the density of dark matter and the properties of dark matter, which is a question that people continue to ask day in and day out for the last 40 years. Let's hope. It's difficult to measure this fog of photon from our neighborhood because we have a photon maker of our own that outshines this. So how are we going to measure a dim background of photons if we have this huge burning ball of gas really close to us that's producing those exact same photons? We also have reflected photons. We have photons that are produced by every star in our own universe. We don't want to know that type of photon. We want to know the photons produced from other galaxies and other stars and that are everywhere in the universe. So we use blazars in order to study that fog of photons. And that photons, again, those are blue light. It's not important. Okay, so how we actually study that, why would a very high energy astronomer who's interested in gamma rays care about blue light photon fog? Well, because if you have enough energy and you have a very high energy photon hit and interact with a blue light photon, so one of those photon from the photon fog, you miraculously, not really particle physicsy, get an electron and a positron. And then that electron and that positron are not observed by Veritas, so this photon that it was originally coming from a blazar won't actually make it to us. And this energy of photon, for a very high energy photon, this blue light right here is the perfect energy for that fog of photons between the sources and us that were produced by all the stars in the universe. So what that means is you have a blazar, it has a jet and it's producing very high energy gamma rays, and let's say this jet has produced 3 photons. They produce more than that, but just for argument's sake, there's 3 photons. And then there's this fog of low energy photons throughout the entire universe. Some of those photons, very high energy photons, make it all the way to us. We detect it. However, some of those photons interact with this fog and you produce an electron and a positron pair, and so you never actually observe that photon. So if you know how many photons this source should be emitting, and you know how many photons you've detected, you know how many fog photons were interacted with. And that gives you an indirect measure of this density of photons. So if you have a low amount of absorption of those very high energy photons, you know that the photon density from starlight is low, and star formation started late, so there's lower clumping of dark matter. Or if you have high absorption of these, then you have high density of starlight. Those very high energy photons don't make it to us very often, and so stars started forming early and you have high dark matter clumping. So you can actually use what you observe from these sources in order to study dark matter, which everybody wants to study dark matter, so I had to put that in there. That is the end of my talk, and I could go over this in summary, but you guys can read, and I want to leave the floor open for questions. So with that, thank you for your attention, and I'm happy to answer questions. You intimidated them.
I did, didn't I? Somehow. I don't know. Gordon.
When Veritas is running, how many events might you detect in a night?
So we have an event rate that's 300 hertz. So that's 300 events per second.
Per second?
Yes. And I would say about 299.9999 of those are background. So our brightest gamma ray source gives us 8 gamma rays per minute. Yes, and so we take a rate that is 300 hertz and break it down with fitting the ellipses to those images to 8 per minute for the brightest source. And then we're capable of detecting sources that only give us 0.8 gamma rays per minute. So No, 0.08, sorry, 1% of that, 0.08.
So your hypothesis is that you're losing a lot of the gamma rays that you could be detecting through this like fog in the universe?
Yeah. Yeah, fog, optical fog, which we know is there, and we know that interaction occurs for sure. So the hypothesis is true. It's just a matter of how many of those photons we're losing to that fog.
You say there are mysteries regarding how blazars produce radiation. Do you have any hints?
There's many, many theories. Depends who your best friend is. No. There are theories that are, it's the mysteries regarding how they produce very high energy gamma rays emission can be broken down very generally just into, is it a population of energetic protons and hadrons, like nuclei and stuff like that, or is it a very energetic relativistic particle population of electrons and positrons? So that's the general breakdown. And then within each one of those paradigms, you can get into the nitty-gritty of, well, this says that it's interacting with an external photon field, and this one says that it's interacting with its own photon field, and this one says that it's like, the details are so far more than we are able to prove or disprove with our capabilities these days. So our first question needs to be, is it protons or is it electrons? And once we answer that, only then can we start breaking the question down further.
I have a question. My question only makes sense if with something that I didn't actually look carefully enough at the diagram. But you have the synchrotron radiation, and you have the
Inverse Compton.
Yep.
Yep.
Depending on how these are scaled, there's something interesting to me that they have the same sort of flux per hertz. It looks to me, I mean,
You're
they're
saying
maybe
this
off by
peak
a
is
factor
about
of
same
10.
as that?
Yeah, I mean, that to me looks like some partition of energy in these physical processes which are different, and yet there's some partitioning of it in a physical process that this could be off by, looking at the widths and so on, but the numbers of orders of magnitude, I can find it is an interesting coincidence that they're as close as they are. Is there anything to that?
For this source, they happen to be about the same, but they have been phenomenologically categorized that sometimes this peak, depending on which source you're looking at, is far subdominant, and sometimes this peak is far subdominant, depending on what subcategory of object it is. So we have been able to say, okay, well, there's different objects based on how bright this peak is compared to this peak. But then if you ask what the physics behind why those peaks differ is, again, another open question. I leave you all with many, many questions, then not very many answers. But you're right, it's an energy balance. What's mainly causing your peak here is an energy density of magnetic field. And then what's causing your peak here is kind of a density of particles, roughly speaking. So you can get information about how strong is your magnetic field and how many particles do you have based on these. But then there's intricacies that can go and change those a little bit.
I had a follow-up, which, that's not really a follow-up, but it's another question. It's interesting when you have a countable number of sources, what your science is like. Do you have any comments about what it is to study blazars where your community knows, oh, that blazar and this blazar and so on? I mean, that definitely happens in other aspects, but there are some fields where they're incountable, innumerable.
Oh, of course. So the short answer is that we understand that we have an ridiculously high bias in the sources and source types that we're detecting. And we heavily utilize other instruments, X-ray and gamma ray Fermi, as well as other ground-based imaging, similar to Veritas, to say this source is bright in gamma rays. Look at it now. And so we're getting very biased measurements of this peak right here, where it always tends to be bright. And there might be a special physical process that is changing how bright that source is getting, and we're only looking at these sources when they're bright. Now, you can only detect them when they're bright sometimes, and so you have to have that bias, because otherwise you're just going to have no peak here at all that we can detect, and you can't study, at least in depth, something that you can't see. So there's a challenge to our sensitivity these days, and that is that we are looking at a population that is countable, that has heavy biases. And so we're still trying to collect the fruit in the basket before we actually study the fruit in the basket.
So what percentage of the Veritas blazars are seen by Fermi lab?
100%. Fermi Lab has detected 2,500 blazars, and we have detected 100. So once you get up to higher energies, which is what Veritas and other instruments like this are sensitive to, that makes them very, very special. For whatever reason, they become special enough that we can count them in the hundreds, whereas Fermi is getting to the point where you can't remember the 1,000 or 2,000 names. But I could tell you, if you really want to bore yourself to sleep, the name of every single TeV, or very high energy blazar. They make fun of me in my collaborations because this one's PKS 1424 plus 240, just in case you were curious.
First of all, I want to say you're one of the best speakers I've heard so far. You're very clear, you're a great thinker, easy to follow, and I really appreciate it.
Thank you. Oops.
Second of all, I've been following with interest the whole thing with the LIGO discovery of gravitational waves.
I knew it was going to come
And I
up.
was thinking with two swirling black holes, would that be a point source for gamma ray radiation through the study?
So this is a very, very interesting question. If you talk to the Veritas collaboration, or I would say any electromagnetic detection device or collaboration, they'll say, oh, it's very important. You have to have electromagnetic signature. It's going to add to the science. It's going to be huge. So LIGO is going to detect something, and then we're going to be able to follow it up very quickly with these instruments such as Veritas and Fermi. And in fact, Fermi has already published a paper on that event. They have a marginal significance in that error circle of LIGO. So there's possibility that these events will have electromagnetic signatures. But then you talk to the LIGO folks, and they will say you don't necessarily have to have an electromagnetic signature of two spiraling black holes. So, of course, LIGO is going to open up something that's completely new and different, and we will learn things that we never thought that we would learn. I would like to put forth the analogy that if you went back to the day where they thought that the world was flat, and you said, what do you think about the fact that someday you're going to learn the world's round? They would all say, whoa, 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 whoa. That doesn't make any sense. You're crazy. So we can't even put forth theories of what LIGO detection of gravitational waves are going to tell us because we can't even think in that kind of framework. But I think that this instrument, as well as other electromagnetic instruments, including optical, radio, X-ray, everybody that's out there, will have the ability to follow on the legacy of the LIGO detections and be able to say something. Even non-detections will be interesting because that tells you something about the physical process. But the real cherry there is the LIGO detections of these events. Hope that answered your question.
Could you say a few words about this intergalactic magnetic field? Is it homogeneous? Is it noisy? Is it swirling around?
Is it? I don't know. That's about as much as I can tell you. So there's just questions about is it homogeneous, meaning if you looked in this direction towards this galaxy, would you have a higher magnetic field than if you looked in this direction towards this galaxy? And then there's questions even more fundamental of where did the magnetic field come from in the first place? That means that these galaxies at some point, which we know when the universe was much more compact, there was charged matter that was moving around and producing a magnetic field to begin with. And then you expand that universe, what happens to the magnetic field and that energy that's stored in the magnetic field as you have the universe expand. These we don't know, but you can study these type of things not directly because you can't see a magnetic field. That a magnetic field is not visible to any instruments that I know currently. So you have to use sources like blazars and then take the processes of while those photons travel from that source, a galaxy, to us, and then make assumptions about the magnetic field, the photon density that they're traveling through, and questions about cosmology. You can only study the source behind the cosmological fields to answer questions about the cosmological fields themselves.
So you said you have a collaboration between all these different telescopes, like radio telescope, X-ray telescope. Does it matter where they're located on Earth?
Well, sometimes they're sleeping when I try to email them. No, so they have to be in the northern hemisphere, all of them, or all in the southern hemisphere, or in space. Fermi's always got that going for him. And And they have to be relatively close enough so that the sky is dark at the same time. And so the sources, they're looking at them at the same time instead of the sun is out during our observations.
Observations then.
Yeah. So it's very challenging, and when an event happens, it really is amazing that you can have interactions and email and all of these things going back and forth in between these scientists, and they really are striving to get the simultaneous data, but then half of them have bad weather, and half of the people don't get to detect or observe the source, and so you have this challenge, or their instrument breaks, or there's always challenges from making multiple perspectives and multiple views for these sources, beyond just the challenge of working with international collaboration.
What's the cost to build one of the detectors, and does it make sense to build a fifth one to get more sensitivity, or?
The cost is really, really, really expensive. More than $1 million, no, $1 billion, a couple billion, yeah, exactly, a couple $1 billion. And so it's a couple $1 billion to build these, but the first one was the most expensive, and then we kind of got the hang of it. And it's not engineers that are building these. It's physicists who are, they're learning the process as they're doing it, and graduate students and stuff like that. So the labor is cheap, but the labor is not so technically advanced. And it's interesting that you ask, should we build another one? Because that would make us more sensitive as we build more. More telescopes of this fashion will give you higher sensitivity. And there's a huge push within the US and internationally in order to build an array that has 100 telescopes instead of the 4 that we have. Now, the international community is a little ahead of us on this. They've already said, here's the money. You guys can go ahead and build it. The US has not so far been thrown into the bucket as much as they should, but the scientists that are part of Veritas and expanded beyond that are pushing to produce a prototype telescope that would go into this array, and that prototype is being built on the site. Actually, I can show you exactly where. If we go all the way back to the beginning. So our telescope, there we go. They're building a prototype telescope right there. And that prototype telescope is going to be much larger than these, so we'll have an inhomogeneous array. Since the analysis was so easy and straightforward previously, why not throw in a whole new telescope that operates completely independently and build it right there? So they're just using that telescope to investigate how you would make the next generation kind of Cherenkov telescope, like Veritas, but better. And it's very expensive.
Besides lightning, does the weather affect this work much?
Yes, even if there's tiny wispy clouds in the sky, because our calorimeter, we're a particle detector in bottom line, and the calorimeter, which is the thing that holds the particles that we study, is the atmosphere. So we want the atmosphere to be as constant and well-known and well-behaved as possible. So if there's more moisture in the atmosphere, it changes how the showers develop. If there's clouds in the atmosphere, it changes how the showers develop. If you have clouds, it also adds some night sky background in the blue light that's coming from Tucson and Phoenix even. So there's a lot of troubles. And even the moon, these are so dim, these flashes are so dim that the moon is too bright for us to operate under full moon. So we operate only under dark skies and good weather. So our duty cycle, we are only able to operate about 30% of dark time. So it's very low. But with that, we do pretty well.
We'll have one final question. Steph.
Oh, this is just a quick, but being in Arizona in that location, you got a good month or two of lots of thunder.
Monsoons, and we unplug everything because the electronics are extraordinarily expensive. And one thing that you can't see is that onto each of these buildings, there's huge lightning rods because we would like the lightning to hit those rods when everything is not plugged in instead of hit our nice little telescopes and ruin stuff. So for 3 months, we don't even bother operating because it's crazy weather. And we're the only instrument of the 3 in the world that has and suffers from these monsoons. So we have, it's unfortunate, but the sky is so good the other 9 months, it's worth it.
Yeah, I know the severity of monsoons there.
Yes.
So.
Thank you, everybody.
Let's thank our students.